It's actually truly an honor to hold this next session. It's going to be the warm-up act for the next gathering. So we're going to ask a few experts in the field of building actual nanoscale technologies, building buildings that can build nanoscale technologies, to join us. MIT Nano is a facility, you will see a quick video of it at the end of our panel, that was built right in the heart of the MIT campus. Building 12, right next to the MIT Dome. Recently, we have just put forward the news that the building will be named after Lisa Su. Dr. Lisa Su is the chairman and CEO of AMD. And the naming ceremony will be in May 14th. Please join us for it. We're extremely proud, extremely happy that Lisa's name will be adorning the building. The building itself is an incredibly powerful space. It is the cleanest, the most quiet place in Northeast and beyond. It's performing at levels that have been previously unseen on any other site on MIT campus because the building itself was engineered from ground up to manage nanoscale, manage it in extremely powerful ways. So I'm going to ask my colleagues to join me, the ones who actually constructed, designed, thought through the building, and has pushed the designs that led us to the sustainability. And I will very quickly introduce them. They'll join me here on the stage. Excellent. Well, we have the architect, the chief architect of the actual construction. Oh, here we go. We'll set them up. I'll be speaking about them as they are being mic'd. Samir Srouji is the AIA lead AP, which means an architect extraordinaire who perfectly understands how to make the most, not just engineered for nanoscale building, but also lead engineered building. The building itself has been certified as LEED Platinum. To our knowledge, there is no other facility of its kind that's been able to reach that energy efficiency level. Now, the reason why we have that energy efficiency level is indeed because of the joint effort between all of us. So PJ Johnson is from Turner Construction, and indeed it has led the actual implementation of the amazing ideas that the team at MIT, together with HGA now architects, I was going to say Wilson Architects, as they used to be known back in the day, have been able to imagine. So the result is that the conversation between PJ, Samir, Julie, and Travis, and me on the side, led to a whole set of insights into how to actually design a building that can manage, sustain extreme performance for the nanoscale as needed. Julie Newman, that I mentioned, is a lecturer of environmental planning and sustainability and director of MIT Office of Sustainability. Julie might have been an odd duck when we started the project, where her tremendous push for sustainable design and the need for the campus to embrace it was just beginning. Mind you, we started the construction project in the early 2010s. So 2011, we started the idea of the project. 2012, we have identified the architects and started working with the actual idea. And the building was constructed and opened in 2018, 6 years later. And then my very dearest of friends with whom I spent countless months and days in just joyous discussion of HVAC and many other glorious things as a professor I never knew I'd need to know. Travis Wanat. Travis is a senior project manager of campus projects. He's a part of the MIT Department of Facilities. So this is what I would like to do with in this panel is strike a discussion between us on thinking through how to actually engineer a built space that is meant to support exploration of the next level of science innovation. In this case, the next level of nanoscale science innovation. So maybe I'll start by focusing on Travis and Julie, on sustainability. I mentioned already the facility itself has been designated as a LEED Platinum facility.
That's true.
How come?
We have the plaque to prove it.
We do have a plaque to prove it, and it took a little while to get it, only because you took meticulous effort to think through the process of what would it take to actually get it. So could you reflect upon it? Because building a highly energy-intensive space like MIT Nano, one that is meant to utilize a ton of electricity, expel the most poisonous gases in the atmosphere, and yet abate them, deal with the energy footprint to be reduced, what would it take to get there?
I miss these conversations. Yeah, so obviously the last thing that you would think about is sustainability and energy efficiency when building a...
Careful.
Typically.
Back then.
Yeah, before I met Julie. When thinking about building a facility like this, obviously it was a huge undertaking for MIT to support and start. So the performance of the building was paramount, and we were, that was part of our mission from the very beginning. But just as equal, we were challenged to make this the most efficient research clean room facility in the world, and then that changed to the universe at one point, so I'm not quite sure. So in an effort to do that, we had to have members of the team from the design side and the engineering side and the build side at the table early. And we took an extremely arduous exercise in identifying every single potential energy conservation measure early on during the design phase. This ended up being a bed sheet of 167 different approaches that weren't necessarily new, but applied through various other building technologies. And as we went through, we took the time to identify what the big markers were and also the conservation measures that we would actually be able to apply and install. So that got us down to like the big 8 ECMs. And then once we got to those big 8 ECMs, we spent even more time looking at, okay, how does this work? How does it apply? And also, how do we measure it, right? Because measurement is a big piece of it. That was the first real step.
Well, balancing the sustainability goals versus building performance, though, always is an issue. And yet, we are actually at the moment, just so you know, when the new tool makers give us the new tools to put into the building, and they tell us this scanning electron microscope is supposed to perform at a 1.2 nanometer resolution, no better than that. We plug it in, we turn on the instrument, we start measuring, and we see features down to 0.8 nanometers, much smaller than what the nominal spec is. We go to the makers and they say, that's impossible. And we invite them to come into the building to see their instrument working there. This happened multiple times now. The building is magically performing beyond what others have expected is possible for a building built in the middle of a city next to a busy couple of highways and indeed roadways that are performing. So how do you match the sustainability, because the building is LEED Platinum, and yet still reach the high performance?
I mean, I'll just tell a little bit of the story, but I'm going to look back to you on the technical side of things. So as Vladimir said, as you can tell, we're all still friends. I arrived in 2013, and you were already about 4 years into it. And I think the interesting messaging for folks on that front is we were literally launching, I was brought to launch an Office of Sustainability, start to direct MIT towards a climate commitment of sorts, although that wasn't even on the table quite yet, right? You were on that committee. And so to land in this and see this as a great potential to actually be the compass, to really set the direction on where MIT could go. So again, the take home there is that you don't need an aggressive climate action commitment or aggressive LEED standards to build a building of the stature that we've built. This actually helps set the guidelines for where MIT could go beyond anybody's imagination except for theirs at that period of time, right? So just to level set on that, at the time MIT committed to this, we were committed to a LEED Silver certification, if you will. There were maybe 3 buildings that were in the works. Sloan, I guess, was at LEED Gold. We did not have a commitment to greenhouse gas mitigation. We did not even have a greenhouse gas portfolio at that point. But we quickly were able to collect that information, and thanks to the partnership we all built, I do feel like I was able to say, I promise it's coming. We will have a portfolio. We will set a commitment. We do need aggressive standards. And so I really believe what happened was building a partnership to use Nano to help elevate a process. And if there's time for a slide, looking at the table, just the overwhelming nature of the ECMs, and setting a process in place to evaluate those, and then looking at the life cycle cost and putting that right into the decision-making process. And so this approach now has impacted, again, I'll look more to Travis, so I don't mean to overstate, but my understanding is this approach and this far-reaching commitment to LEED Platinum on a clean building, on a clean lab, has now set the stage for every other building on campus. And we have since now committed to a net zero. We have a net zero 2026 commitment at MIT and a zero emissions by 2050 commitment. And with a deep awareness of measurement and verification and understanding the implication of every single building on campus, and constantly studying and trying to determine how are we going to get to zero emissions by 2050, even with this building, on campus. So it's pretty remarkable.
And we started with the hardest program to do that with, right?
Yeah.
So this is a benchmark, and that bed sheet there is only possible with having the resources in the area, and we're lucky where we are to have construction managers, designers, and engineers that understand the importance of it, right? Yeah. So having the support of the Institute to take this serious and support it, because it's a lot of effort up front and it's not traditional, and have the people at the table, and PJ and Samir can talk about that as well. That's critical. It's critical.
Samir.
So you mentioned kind of the high performance in terms of nanotechnology, and then high performance in terms of energy. We were quite good when we started MIT Nano Design on getting high performance from vibration, noise, because we've done a few. So we knew that we did it at Harvard. It was performing really well. MIT was the biggest user at Harvard at the time. But when MIT, both from Vladimir, Julie, and leadership said, you need to make this the most efficient clean room, this was a new challenge for us. And that took us on this journey and research to figure out what is the highest, the kind of efficiency level that is there. What do we need to focus on to get us to where we got? So that, again, took a collective effort to get there.
Yeah, well, as I remember the discussions, the construction industry is very conservative. You need to build something that I can go to, and 100 years from now, it will still work, right? At least 20 to 30 years from now, it will still work. And yet, we were tossing ideas that were fairly esoteric. I mean, I think at some point I was talking about using geothermal to cool me down, and there were a helicopter pad that Travis never gave me that I need, all kinds of things that we were going through. So, PJ, from your perspective, as you started looking at this particular project and the oddities that we were tossing your way, what was it like to actually go through the process as a construction guy, constructing a space like this? And then the other one, as you look at this, are there lessons you can pull out and say, that was crazy, but it worked really well. And as a result, my next project might want to be influenced this way.
So I was lucky, as Samir said earlier, got a chance to work with both Travis, and Samir on the Harvard LISA project. So we did take some lessons learned from that project. I also did a nano facility up at UMass Lowell, brought those lessons learned, and then we had this team that really came together back in 2013, 14, at least when Turner Construction came on board. And it was, the great thing about that team is it was truly built on trust, and people could throw out ideas, and we'd look at it, I'd look at it on the practicality side of things. How am I really going to construct this? How am I going to make sure that what Dennis, Vladimir, and MIT is looking for performance, inside the laboratories is we can actually achieve that. And we had some great conversations where we would bring in the experts into the room, myself and the people pouring the concrete, finishing the concrete. I remember Dennis saying, these plinths need to be smoother than a pool table. And
he was talking about 1/8-inch tolerance.
Millimeters. And so we're talking about that really tiny line on the ruler, and these are the guys finishing concrete. And it was these amazing conversations that we had very early on as we were developing the plan, and really, I would say, behind the scenes, kind of putting the fear of God into the actual workers constructing the building, because, hearing how the building needed to perform and hearing it, put into layman's terms from, people like you, Vladimir, so people could understand why it was so important to get down to that tolerance. We really got to a good place, with, those imaging suites, and, obviously, we talk about the HVAC systems. It's developing a system and a process that started really from day one, where quality, was tracked, monitored, managed all the way through, so we weren't chasing an issue when we turned the building over to MIT. We were finding those as they were being, built, down to walking the systems down, watching the material come in, checking it off as it comes in, watching it go in, testing it as it goes, as we construct it. So making sure we weren't covering up an issue.
Yes.
And the other critical part of that, just to jump in there, PJ, is having the operating staff, Dennis, key player, at the table as early as we did. Having that input, understanding how the building was going to operate and what he needed to do while we were designing it, and even through the course of building it, at the time was trying, but at the end, I think it really gave us a better product and a better design as well.
Yeah. Dennis is Dennis Grimard, the managing director of MIT Nano, and actually a key individual in driving the technical norms that MIT Nano needed to live up to, and indeed the team implementing it. So the building itself was designed on a piece of paper, sketched out, and built to the accuracy, as I recall, of a 1/4 inch. Is that true? Like everything that, all the pipes have been roughly laid out?
Yeah, in the BIM model, we learned the lesson that you need to actually model everything down to the 1/4 inch size to get it right in the field. So that, yes.
The other thing that stunned me, as I recall, is to build the space and maintain its cleanliness. After pouring concrete to outline the huge 40,000 square foot space that will become a clean room, that is the day after the construction guys were wearing booties on the site to prevent dust from spreading. Is that true?
So, yeah, I mean, I learned the term latent contamination, right? Which is, it's all that dust and debris left behind by the construction, process that could contaminate the filters and, your system. So we developed a process from day one where, once that 40,000 square foot envelope got built, which was the drywall. Basically, it was the drywall went up. That was the last dust generating activity. We had laborers in there every day wiping from the top down as we built, so there was no dust left up in the up in the nooks and crannies that could ultimately foul your systems. But first time I met Dennis, he came in and said, "PJ, what are you going to do about latent contamination?" I was like, "Okay, well, here we go." But, a great relationship, and but it was the process, though.
Oh, it was, but I'll tell you that when we turned on the building, there were places, it's meant to be class 100, which means out of 1 million particles in a cubic foot of air that are bigger than half a micron that we typically breed, only 100 remain of the million inside the clean room. That is what it's meant to be. There are plenty of places that when we stepped into the clean room, we were at 1 or below. There were simply no particles. Thanks to the latent contamination.
And the fear of God we put into the contractors that they couldn't, dirty up the area. But yeah,
right. So it sounds like the fear of God is important.
That's good. That's good.
Build a
appropriately.
All right. Please.
I think one piece that you're reminding me of that with that discussion is what I really appreciated, and I think which is another lesson learned, which then applied to future buildings, was the ability. Typically in a role like mine, you step into a design discussion like that, and they say sustainability versus cost, or sustainability versus access to material. Everything's a versus. And I became accustomed to that and how to kind of, de-escalate those discussions. But thanks to the vision and the ability for this, I mean, clearly this group had worked together before as well. But I think that was a key ingredient, is to let go of the verses and say, how can you build the cleanest, best clean room, and go into Vladimir's vision in the galaxy. I'd go beyond world with Vladimir, and think, how do you build the cleanest, most sustainable, add all of those pieces together so you're integrating that vision, as opposed to how do you build the cheapest, most sustainable, or how do you build this versus that. And as soon as you remove the verses, you end up with a totally different viable product. And to me, that's what you guys prove you were able to do.
To add to that, for us as the architects, designers, you had to do all of that, no verses, but still bring the poetry of architecture, design, how you bring light and make a beautiful building.
Right.
We just, today, I can announce that we just won another award, design award, for the MIT.nano.
Wow. Awesome.
I can tell you now.
Well done.
Wow.
This will be number 10 or so, or
Amazing.
Yeah, it's
Yes.
a significant number.
It is significant. This is from the SCUP.
Wow.
Society for
Congratulations.
College. Yeah, thank you.
Vladimir, you mentioned the model, the 3D model that we built. I remember Wilson. Early on in the process, they said, so this is going to be a machine that's visible to everybody. So this isn't a back of the house type of mechanical room that you're building. This is, you open up the hood of your Ferrari, and that's how it needs to look. And we had well over 100 coordination meetings, actually putting those were actually together, going through those models to make sure everything was down to that quarter inch. But
it's a lot of investment of time and some amount of incremental money as a result. As I recall, maybe it was 9 months to go through the 180 different options you said were considered.
Yeah, 9 months. I mean, it was an ongoing process.
Yes,
but I wanted to add to the important thing about that, right? To say you're the most efficient research clean room, you need a baseline or a benchmark, which we didn't have.
Exactly.
So in order to build that list and build that model, we spent about a year traveling around the country, going to various peer institutions to find out what information they had that they were actually measuring, that we could then start to build our baseline. And we found out that most places measured parts and pieces, but not the whole pie. So that helped shape what we had to focus on. And now that we have the building built, we've incorporated the ECMs that are the biggest players. We've also taken the effort to install the measurement devices to take those readings. So we have real data, we have a real baseline, a real benchmark, and hopefully I think what's happening now is other places that are starting to upgrade their research facilities or build new ones are using MIT Nano as the new benchmark.
It is definitely the golden standard now.
So actually, I was looking at the data just the other day. The energy consumed by the old micro nanofab, Building 39, is comparable to the energy consumed by MIT Nano. And the two are about 10 times different in size, roughly speaking.
Yeah,
roughly. It's truly impressive. But Samir, you emphasize the fact that you need to build a space that's functional, and it's performing extremely well to allow us to see the atoms. The other part of this space that you also built is the cultural norms that needed to be built into the campus to allow us to actually cross the scientists that never saw each other and provide pleasant, comfortable places for all of us to embrace. You succeeded in that. And you need to take, I guess the first question is, what took to do that? Because at the end, it's not just that you build any building and it's pleasant. It has to be understanding the culture it's going to be residing in.
Well, it takes the intention and kind of understanding the culture that you're trying to produce. As people noted, the building is really a machine. So 90% of it is the clean room, the laboratories. So we only had the edges to work with, but it was important to just insert the right type of space to foster interaction, visibility. There's a lot of glass. Typically, you don't put a lot of glass in a clean room because you're dealing with humidity and condensation and And then an open stair. Our fire stair was designed to be an open and very visible place for people to move up through the building. So it's easier to kind of connect people on the ground level and have interaction spaces. And the East Lobby is a space with booths and seating kind of that is comfortable, that is kind of rare in the campus. So it's lovely to see it active so much. And the moment, what you call the moment, which is kind of setting the view onto the rest of the campus. Architecturally didn't take that much. It's the intention, the thought, and trying to kind of capture that culture.
Yeah. Well, and just let me ask you one more question, because much of MIT Nano needs to last till 2050, the way it is right now, right? So PJ has built it really well, with latent contamination not being there. The vibration is extremely low. The campus is growing around us, and we are indeed able to still maintain the extreme quietness. We can pick at the noise of the elevated highway trucks on I-93. We know when the trucks passed, we can pick those out. That's the only noise that's underground of MIT Nano, and we eliminate it to not mess our measurements. Instruments can see down to 80 picometers in resolution. That's 0.08 nanometers. Really good, let me tell you. But Samir, you're gonna have to build one more building, right? Tomorrow, I'm sure another client will come and say, hey, I need this to last till 2060. How do you keep with the times? How do you keep with the next set of challenges that you need to integrate? What is there, a conference and encyclopedia that gets issued every month that says, here's the latest set of coolest things that you can add as bells and whistles to the next building you're going to construct?
There are. You have to keep up. This conference, I've learned a lot of what's happening at MIT Nano that is going to inform our glass that we use in the next generation of buildings. So that is valuable stuff. On the sustainability front, we are moving the goalposts with every project, because you cannot settle with what we did at MIT Nano. The next client is going to say, how do we do better? Yeah. So that takes further research of where you can dial and put the teams to achieve it. So yeah, have to keep up and learn from every project and every other competitive project that.
Every side of the project team now is pushing for that, right? So the contractors are pushing for it, right? The design teams are pushing for it. It's the typical thing. I used to say the normal. It's the norm, right? So everybody's bringing these ideas to the table, looking at embodied carbon, looking at ways to reduce it, looking at more efficient approaches. So when all three legs of the stool are working in the same direction, it certainly helps to create that innovation. Awesome.
I notice there are questions on the screen. They're just a tad too far for me to read. I wonder if you can probably find the ones you're particularly excited about. Oh, there we go. How do you mitigate vibration from the Red Line subway? Oh, goodness. Any thoughts?
Well, the first thing we did, just from a passive approach, was we had 5 spots on campus that we measured for vibration and EMI. And the Red Line obviously sort of surrounds us. And so that's why it landed, our site landed right in the middle of campus. So we couldn't completely passively mitigate it. So there is some active cancellation. I don't know if it's up and running all the time, because there's issues with that too, but there is an element of active cancellation as well.
Well, the very first step, as I recall, PJ, is you asked 100 cement trucks to come in a row, kind of what I call the ballet dance, because the cement hardens or concrete hardens in half an hour, right? So
about an hour, yeah.
Yeah, an hour. So, and 100 trucks pouring 5 million pounds, as I recall, of concrete.
Yes, yeah.
Yeah. So what we did, you get down to the bottom of the imaging suite, and it had a big mat slab. Ended up being, it was about 4 feet thick, and mat slab underneath the imaging suites. Then on top of that, you build your plinths, the concrete plinths, that the the microscopes sit on. But what we also did was we took measurements at the bottom of the hole once we got to the bottom. Then we poured that mat, and then took measurements there again, and to see if the foundation, so the slurry wall, and the mat foundation were doing what it was supposed to do at that point in time. Then put the concrete plinths, took another measurement there. Is that doing what it needs to do? But then the other thing we did was, as we turned on all the different systems and pieces of equipment throughout the building, we took measurements at that piece of equipment, and then also again at the sensitive tool location, so we could see how that vibration decayed over, over that space, or that length. And then we could also, Dennis has a log of the characteristics of the vibration that piece of equipment puts onto the building. So if something ever goes wrong in the future, he knows he can actually find, okay, that's the pump, with the chill water system, or whatever it might be. He could actually, it could help troubleshoot in the future.
So the 5 million pound slab sits surrounded by the slurry wall. Slurry wall itself already is arresting some of the incoming noise.
You got it.
The slab itself is not actually connected to the slurry wall or to the rest of the building. It's floating.
It floats.
And the building itself has pillars that support the rest of the building, but they don't touch the floating slab. They go through it and land on their own landing mats, right?
Correct. Yeah, so there were a lot of isolations. We even broke the slab from the microscope suite to the northern half of the building, where a lot of the mechanical rooms were. But you do need to still bridge it, but you need to come up with a way to isolate so the vibrations don't travel through the concrete.
Well, it's working well.
So, which is great. It's awesome to hear.
All right. Let's see, we have a couple of more minutes and a couple of more questions. Is MIT Nano Building installing the new solar tech that we talked about today? One day, as we mentioned, I believe Miles was asked at the very end, is the tech commercially available? It's not yet commercially available, but given the fact that they have a capability of printing on 3 meters by 1.5 meters or 10 feet by 5 feet type pieces of glass, that's just about the size of our windows. And consequently, we can easily install some of these on the back side or front side of our windows. It'd be a great addendum as long as Samir lets us, because we need to make sure we keep the aesthetics that he particularly likes. Good question, though.
Yeah, and we are using the campus as a test bed, so as soon as Vladimir rolls out one of those solar panels, we are ready.
Coming up, Julie.
Okay, good.
All right. Does building a high-tech facility like this, like MIT Nano, influence how you approach non-lab projects now?
So one thing we learned through the kind of submission for the Code Top 10, the AIA coveted award, is that tying high design, high performance to environmental responsibility and social responsibility became a lens we look at all our projects with. HDA adopted that framework for all our work. So it comes from MIT Nano's experience.
All right. We are concluding. Samir, PJ, Julie, Travis. Thank you for building what you built. There are many great things waiting for you to still construct. So
we hope so.
Get to it, my friends. You're amazing. Thank you
so much.
Thank you.
Good to see you guys.